Hi. Today we'll just continue what we started on oscillatory motion. There's one part which I didn't cover yet. It's the graphical part. And if you remember, it's the second example on the sheet I gave you, example number 2. So I'll take the same example and try to discuss it in general. So if you remember, we had in example number 2, a graph of acceleration time. So in this example, we have a simple harmonic oscillator, a spring oscillating, and it oscillates in such a way that its acceleration changes with time according to this graph. Yeah? You can see oscillation graphs are either sine or cosine, yeah? With shift, of course. Sometimes they start from 0, sometimes not. Now, if you have a graph, acceleration time, velocity time, or position time, it doesn't matter, in all these three. The first thing you have to think of is a very important piece of information. Concentrate on this. Each time you have a graph, AT or VT or XT, doesn't matter. Think of finding the period, the time for one cycle, T. So if you have a graph, how do you find the period? It's the time from a peak to the next peak.
X2 minus X1.
Okay? This is a period. Even if you don't need it, always the first thing, calculate the period. So how much is the period here?
5 minus 1.
Which is 4, yeah? All right? 4 seconds. Now, why we find the period? Because remember, period, frequency, angular frequency are interlinked, yeah? They are linked together. So if you know one of them, you find the other. So in this case, if you know T is 4, what is the frequency? 1 over period, yeah? 1 over 4 hertz. Yeah? And if you know the period, you can find the angular frequency, which is 2 pi over the period. And this is 2 pi over 4, which is pi over 2 rad per second. Okay? Now you can see that why the period is important, because you can find the angular frequency. And angular frequency is a key in oscillations. You need it. Okay? Now, let's say you have a graph which is not so complete like this. Any graph, xt, vt, like this one. Let's say you have a graph up to here. And this is 0, 2, 4, 6. Yeah? And this could be anything. Could be x, V or A. The y-axis can change, yes? But the x-axis is always time. Now, the question is this. What is the period of this oscillation? Remember here, I didn't give you the complete oscillation. Part of it.
2 times the half of the period.
This is not a complete cycle, yeah?
This is 1 over 4 from the...
So,
we multiply by 4.
so how much is it?
So it is 8.
8. Okay? the smallest part which you need is a quarter of a cycle. If you see a quarter, then you can find the total, yes? So here, up to 2 is a quarter of a cycle. Multiplied by 4, it gives you the period, yes? So you don't need a complete, yeah? Sometimes half a cycle is clear. So what's the period here? If this is 8, 16, yeah? Second. So you don't need a complete cycle. Right, so this is the first thing here. What is it? Because I know from here to there is a quarter of a cycle. So if you want a complete cycle, times 4. Okay? So now, what you do first, whenever you have a graph of oscillation, find the period first. Time for 1 cycle. Once you find the period, you'll find the angular frequency. And angular frequency is needed. Now, suppose this oscillator is a spring. Now, remember, spring has an omega angular frequency. What is the angular frequency of a spring? Root kappa over m. So when you find the period, you'll find the angular frequency. And then you use the angular frequency with the mass, you find kappa, spring constant. So here, suppose this spring connected to a mass of 2 kilograms. Then you can find spring constant, kappa. And once you know kappa, then you can think energy-wise. What is the total energy of an oscillator? E. Half amplitude square. So for energy, you need spring constant and amplitude, yeah? So how do you find the spring constant? Omega for a spring, root square of kappa over m, all right? So you can see that I started with what? One piece of information, the period. Then I found the frequency and angular frequency. And then angular frequency, this is general. But because it's a spring, then spring angular frequency is root of kappa over m. Mass is known, you find kappa. Once you find kappa, then you can find other things. Like, if I ask you what's the spring elastic potential energy, what do you need? Half kappa. Look, you need kappa. Of course, you need x as well, and a. All right, now, this is a question now for you all, but don't talk, just write the answer somewhere in your notebook. For this oscillator, acceleration with time, what is the amplitude? Don't answer, write it down. How much is the amplitude? Capital A, amplitude. What is the amplitude? Just write it down somewhere, the number or the calculations, and later on we'll see if you got the answer right. What is the amplitude? Don't look at the solutions. Answer it yourself. You got it? You have an idea? Okay. Now, raise your hand if you think that the amplitude is 4. 1. If you don't raise your hand, so what do you think? What's the amplitude? Something else? Okay. So what is the amplitude? 1? Amplitude, it's capital A, amplitude. How much is it? 1? How did you want? Where is the 1? This one? This is time.
It's the maximum point.
I know, this is time. Amplitude is maximum x.
Yeah, maximum x. This one is.
This is not x-axis, this is time. Not every x is x. This is time scale. 8? Where is 8 here?
From the minimum point to the maximum.
Where is the minimum point? Oh, you mean from here to there? This is amplitude? The rest? 4? 4? Who agrees is 4? Raise your hand. 1, 2, 3, 4. So 4 and 4 agrees, yeah? What is amplitude? What's the other name for it? Maximum what? X. Is this X? Is this X? What is this? This is amplitude. This is acceleration. This is maximum acceleration. So if you think every height like this is amplitude, is wrong. When this is amplitude, if this is position, X. Now, from here to there is A max. Maximum.
At t equal 1.
At time 1, we have maximum acceleration, yes? What is the other time where we have acceleration max?
5.
What about 3? Maximum. Okay, negative, positive, that's for direction, but maximum value. And at 5. So what are these? A max. But I ask you for A max or X max? So how do you find amplitude if the graph is not for X? Okay, you go to A max. What is A max equal to? Amplitude multiplied by omega square. Now, you want amplitude. This is from the graph is omega pi square, then you find the amplitude. Okay? What I want to say that is not every maximum is an amplitude. When this is amplitude, if the graph is xt. If this is xt, yes. This is amplitude. Amplitude. But this is not xt, this is 80. All right, so I don't want to see this mistake. It's a common mistake. This is not an amplitude. Now, let's talk about the 3 things which we have graphically. We have velocity, position, and acceleration. Yeah? 3 things. Position, velocity, and acceleration. Now, the way I write them like that, V on its own, X and A together. Put those together in one cycle, and this is on its own. So it's not XVT, XVA, no. Position with acceleration and velocity. Now, in simple harmonic motion, in oscillations, these two, they work opposite. Which means when velocity is max, these two are 0. All right? So when the velocity is maximum, the position is? Why the position? Remember, when something oscillates at 0 position, it has the highest velocity, yes? Like a pendulum. In the middle, how much is x in the middle? 0. But the velocity? Maximum. Okay? Acceleration as well. 0. Now we take the other case. V, 0. X and A both are max. When do you have velocity 0 in oscillations? Extremes. At extremes, what happens to the object? It stops, yes? But the acceleration, it means change in velocity. When it stops, it means it was going to the right, stops, and turn to the So this is the highest acceleration, A max. What else? When you reach the extreme, how much is x? X maximum amplitude, yes? X max. So in summary, velocity 0, acceleration and position are max. Velocity is max. These two are 0. Now, we distinguish between those two groups. Now we come to and compare x with A. Remember, x and A, they go up together, they come down in value, So when A is max, x is max. When A is 0, x is 0. Agree? Now we come to the sign because we have negative and positive, right and left. X, position, negative or positive. Acceleration as well, negative, positive. So now if you compare x with A only, think of the equation which links x and A. In simple harmonic motion, acceleration is minus omega square x. Can you see? When x is max, A is max. When x is 0, A is? Now think of the sign. Of course, when it's 0, we don't need it. When x is max, as example. When x is maximum positive, what is A? Maximum negative. When x is negative, so those two, they work opposite in sign. In value are the same. Both max or both 0. So here you have them, one positive, one. Okay? Now I'll apply this one here on the graph. At what time or times we have maximum acceleration on this graph?
1, 3, and 5.
At time 1, 3, 5 seconds. What do we have here? A? Okay. When A is max, what is the velocity?
0.
So now I can ask you the question. At what times the velocity is 0? 1, 3, 5. Okay. At what time or times we have x maximum negative? Maximum negative.
1 and 5.
When we say x and we want A, use the opposite. Yes? Maximum, what did I say? Maximum what? Negative x. Which means look for maximum positive A. Where is the positive A? 1 and 5. You got the idea? How they work? V opposite both x and A. One max, the other two, 0. Yes? Or those two max, the other one is 0. But the two together, A and X, they just differ in the sign. Values are the same. Either both max or both are 0. Yeah? So this is the part which was not clear. And this will help you to solve the problems graphically. Now you have the example graphically solved, and you have 2 questions in the review, I think. So you need to practice on this one. Now what I want to do here, I'll create questions here for this one. Now, the question, what is the maximum kinetic energy? What is the maximum kinetic energy of this oscillator, which is a spring? What do you need to find maximum kinetic energy? The formula, kinetic max, half V square max. So to answer the question, you need V. Good. This graph, does it give you V max? Where is V max?
When A is 0.
This doesn't give you the value. The graph doesn't, it tells you where you have max and 0. But here you need the value. Okay? Where do you have V max? No, 0, 2, 4. But what's the value? You don't know. You know at what time, but when? I need the value of V max. How do you calculate V max? What is Vmax equal to? You have a formula. A omega. Now you understand why we started with the period? When you know the period, you calculate omega. And when you know omega, you need it here, okay, to find. But still, you need. And A, you have it in acceleration, because acceleration, max, is A omega square, yeah? So if I know omega, and I know A max from the graph, I find, and once I find A, and I know omega, I can find V max, yeah? Right, I want another way to find K max, not using V max. Think energy. E, total energy, is U plus K. So when you want maximum K, U is, so what is K max equal to? Don't forget that. So E is equal to K max. Okay, so now, if you want K max and you don't have these, you have to find E. How do you find E? Half kappa. Okay, in this question, how did we find A? From A omega. Yeah? What is left? How do you find kappa? From omega for a spring. But I gave you the mass here, 2 kilograms, yeah? So then you have E. And E equal to K max. Okay? Now, the last thing is for energy. Don't forget this. Always think of this equation. Why you have to think of it? Because sometimes the question is so easy, you know maybe the total and the kinetic. So what you do? Subtract, you get the potential, yes? And when you know the potential, it means you know X. Because potential is half kappa X squared. Or maybe you know potential and total. What can you calculate? Kinetic. And if you know the kinetic, you can find the velocity or the speed, which you are looking for. So this is about the graphical. Now, the last part, which I covered, but I didn't give you a practice on, it's the pendulum, the simple pendulum. Now, on the review problem sheet, there are 3 questions on pendulum. I think question 3, question 7, and question 21. Question number 3, 7, and 21. What happens sometimes when you have a pendulum question is that you don't have one pendulum. Maybe you have 2 pendulums, yes? Or you have one pendulum, but you use it in 2 different conditions. So you have a pendulum, you can use it on Earth, and then you take the pendulum, you use it on the moon, yeah? Or on another planet. And sometimes you change the length, sometimes you don't change the length, sometimes you change the period, sometimes you don't. So in this type of problems, how do we approach the problem and to solve it, yeah? Think of 2 scenarios. You have a scenario before and after, like you have 2 conditions, before and after. Or first condition is when the pendulum on Earth. Second condition, when the pendulum on a planet, on the moon, or the pendulum on top of a mountain. Changes, yeah? So pendulum in general, we have one equation. The period of a pendulum is 2 pi L over G. What is L? Length of the pendulum. G, gravity, acceleration on the planet. If you are on Earth, this is 9.8. If you are on another planet, not 9. Now from this one, what can you see? The pendulum period is directly proportional to the root of length, not length. So when L doubles, what happens to the period? Root of 2. When L is half, the period, 1 over root of 2. You have a root. Anything you put inside, you'll have the root of it, yes? So if I double L, it means 2L, yes? Which means root of L, yeah? So you'll have a root square, yeah? The period with the gravity, inversely proportional to G. So when you double G, this will be reduced by how much? 1 over root of 2. Okay? When you make this one half, this will increase by root of 2, not 1 over root of 2. Yeah? This is the first thing. Now, how do you use the pendulum in 2 different conditions? This is what you do. Apply this equation twice. Call the first one number 1, period 1, 2 pi, length 1 over gravity number 1. Like when you use the pendulum on Earth, we call it number 1. Then you take the pendulum and you use it on Mars, another planet. So I call it period number 2 pi. The length on Mars, gravity on Mars. Number 2. Then next, divide these 2 equations. You'll have a ratio. What's the ratio? T1 over T2, 2 pi over 2 pi, L1 over G1, L2 over G2. 2 pi with 2 pi cancels. And then I can take this one up and turn it upside down. So it's T1 over T2 equal the radical L1 G1 multiplied by, look, G2 L2. Now we don't like radicals, so we square both sides. When you square both sides, you'll have all this square. T1 over T2 all square. You'll have L1 over G1 multiplied by G2 over L2. I don't like L here and L here, so I'll put them together. L1 over L2, G2 over G1. And this is T1 over. Can you see this equation? This is a concluded one, yes? What's so special about this equation? You have 3 ratios. Ratio for the gravity acceleration, ratio of length, ratio of period. But be careful. 1 or 2 of you will miss this. Whenever you want to solve a question, you miss the square. Okay? Don't miss the square. Another problem is, or something you get it wrong, look, 1, 1, because it's 1, 1, you put this one as well. G is always opposite. 2, because G is inverse. So 2, 2, okay? So if those 2, 2, this becomes 1, opposite. This is something I concluded. So you can solve the problem based on this one. The solutions you have, maybe it's a little bit different. You can always use this. Ask yourself, the first period, what was it? Maybe it says the first period was capital T on Earth. The second period, when we took it to the moon, maybe it's twice of the one on Earth, yes? So what do you say? T1 is T, but T2, twice of? So when you substitute here, you'll have T with T cancelled, yeah? Or maybe you double the length or make it half. Or G as well. Maybe G on that planet is 3 times the gravity on Earth. Or half. Or 5 times. 3 Gs. Half. Same. This equation will solve your problem, yeah? So I think that's for today. And we continue some other time. Thank you very much.